So it is a continuation of video of session 7. So this is now W2 is U2 minus inner product of U2 comma V1 into V1. So this is sin 3x minus sin 3x comma root 2 by root pi into cos 3x into root 2 by root pi into cos 3x. So this is equal to sin 3x minus root 2 by root pi into cos 3x, integration from 0 to pi, root pi by root 2 by root pi into sin 3x cos 3x dx. This is like 2 sin x cos x sin 2x, we can write like this. So this is sin 3x minus 2 by pi into cos 3x 0 to pi sin, here sin 2x cos 2x. So this becomes sin 6x by 2 into dx. So this is equal to sin 3x minus 2 by pi into cos 3x. So if you make k integration of this, this is minus cos 6x by 6, and 6 into 2 is 12, 0 to pi. So if you apply a limit, you can see that the value is sin 3x. So norm of W2 is W2. So W2 is sin 3x. Therefore norm of W2 whole square is W2 comma W2. So this is sin square 3x dx. So 0 to pi, sin square x is 1 minus cos 2x by 2. So according to this, 0 to pi 1 minus cos 6x by 2 into dx. So you make an integration, it gives x minus sin 6x by 6. Okay, 1 by 2 taken out. Okay, 0 to pi. If you apply a limit, you get pi by 2. Again, therefore norm of W2 is also pi by 2. So norm of W2 whole square is pi by 2. Therefore norm of W2 is root pi by root 2. And V2 is W2 by norm of W2, that's equal to root 2 by root pi into sin 3x. Clearly we can see that norm of V1 is 1, norm of V2 is 1, and also we can find out that inner product of V1 comma V2 is 0. Therefore the vectors V1 V2 are orthogonal, therefore they form a basis for V called the orthonormal basis. The V1 is root 2 by root pi into cos 3x, V2 is root 2 by root pi into sin 3x is an orthonormal basis for V. Okay. Now this is the second example of constructing an orthonormal basis. Now let us consider the last result in this section. So suppose V is a finite dimensional inner product space over a field F. Let V be a finite dimensional inner product space over a field F, and let W be a subspace of V. Then we can show that V is the direct sum of W plus W per orthogonal complement of W. Okay. Now let's prove this. Being a subspace of an inner product space V, the subspace W is also inner product space. This you know. And this inner product is restricted only to the elements of W. Okay. Now W becomes an inner product space means what? Every inner product space has an orthonormal basis. Therefore W has also orthonormal basis. Okay. I will let W1, W2, etc. W be the orthonormal basis for W. Okay. Then let V belongs to V and set the vector V0 as V0 is equal to V minus inner product of V comma W1 into W1 minus V inner product of V comma W2 into W2 and so on, minus inner product of V comma WR into WR. Okay. Definitely this element, certainly V0 belongs to V. V0 also belongs to V. Then inner product of V0 comma WI you take for I is equal to 1 to R, this you can find out to be 0 only. Okay. Inner product of V0 comma WI is 0 for each I take the value 1 to R. So inner product of V0 comma WI is 0 means inner product of V0 comma W is 0 for every W belongs to W, because they are the basis means every element of W is a linear combination of basis elements. Therefore V0 comma W itself is 0 for W belongs to W. Now V0 comma W is 0 for a W belongs to W implies where V0 belongs to. V0 belongs to orthogonal complement of W, which is W perb. Therefore V0 belongs to W perb, and these vectors, okay, are belongs to W because they are the linear combination of W1, W2, etc. WR. Therefore V can be written as V is equal to inner product of V comma W1 into W1, V comma W2 into W2, and so on. Last element is V comma WR into WR. So V naught, that left hand side term be transformed to right hand side, that becomes V naught. So this is the first R elements belongs to where? W, because it is a linear combination of W1, W2, etc. WR, and this V naught belongs to W perp. Therefore, the element V belongs to W plus W perp. Now we taken V belongs to W, and we have shown that that element V belongs to W plus W perp. Therefore, V is a subset of W plus W perp. Already W plus W perp is a subset of V. Therefore, we can declare that V is the sum of W plus W perp. Means V is the sum of W plus W perp. Then to show it is a direct sum, let us consider what will be their intersection. So W intersection W perp is 0. Already we have shown. So let X belongs to W intersection W perp. This implies X belongs to W and X belongs to W perp. Now X belongs to W perp implies inner product of X comma Y is 0 for every Y belongs to W. In particular, for X belongs to W, inner product of X comma X is 0 implies X itself is 0. Therefore, W intersection W perp contains 0. Now V is the sum of W and W perp, and their intersection is 0, means what I can say, V is, by definition, V is the direct sum of W and W perp. V is equal to W is direct sum W perp. Okay. So from this we have a small corollary. So dimension of W perp is equal to dimension of V minus dimension of W. This straight away we can declare this, because V is the direct sum of W plus W perp. Therefore dimension of V is dimension of W plus dimension of W perp minus dimension of W intersection W perp. This we have proved, right? This result we know. So this is equal to dimension of W plus dimension of W perp. Dimension of W intersection W perp is what? It contains only 0, means the dimension is 0. Therefore, dimension of W perp is equal to what? Dimension of V minus dimension of W. Okay. So this is continuation part of session 7. Okay. You combine session 7 and you make this, I will call it as session 8. So you combine these two. These are the few results that we are discussed in vector spaces. Okay. Thank you.